Hi, we're going to walk through the 12.2a quiz right now. And the first page or the front page of the quiz is just a whole bunch of data. So again, as we read through this, we just recognize it says, Lupe is shopping for a used car and collects data on age and years and price in thousands of dollars for Ford Taurus sedans on used car websites. On this page is a computer output for 3 different regression models. The first model is price versus age. The second model is the log of price versus age. And the third model is the log of price versus the log of age. And then questions about these data are on the next page. All 3 are log base 10. So what I want to do is I just want us to first analyze the graphs in this first page. So again, Roman numeral 1 is just the original data. So I just kind of want to write some things that we notice about the first part. So Roman numeral 1, this is your original data. And when you look at the scatter plot right here, you notice that it's not linear. So I just kind of want to, again, write down things that I notice. So notice it is not linear. It's not a line when you look at the scatter plot. And we want all of our data as we analyze it to be a line. The other thing that I want you to notice is I want you to look at the residual plot. And we talked about residual plots last class or before. And I want you to also notice that the residual plot has a pattern. So the residual plot has a pattern. It has sort of a U-shaped pattern to it, right? High, then low, then high again. And then the third thing I want you to take a note of as we kind of go through here is the R-squared value. And again, they always write their R-squared value in terms of a percentage. So this is a 98 and it looks like 0.3%. And as you look at that R-squared value, you always want to note how close is it? How close is it to, again, either 100% or if you're writing as a decimal, to 1. So in your original data, again, we notice that this isn't really linear, and as we kind of keep going through our analysis, linear is what we really want to be trying to achieve. That's sort of the name of this section. If you move on to the second Roman numeral, as you look at the second Roman numeral, again, you should notice that it's log price versus age. And whenever you do a x value, so our x value is age, notice the x-axis, and you are taking the log of the y value, so notice that that's the y-axis and it's the log of price, you should note that this is an exponential transformation. We refer to this as going to be our exponential sort of model. And then you want to go through and you want to notice sort of the same 3 things. Note, when you look at this scatter plot, again, you notice that the scatter plot, notice the plot or the graph is more linear than your original data. More linear than original data. Again, look at your residual plot. What do you notice about the residual plot? The residual plot for Roman numeral number 2, or for, in this case, our exponential model, is much more scattered. And if you look at the values of the residuals, these are only in tenths, where the first ones were in whole numbers. So the residual plot is more scattered, and the residuals themselves are smaller. The residual values are smaller. And then again, that third thing you want to look at is that R-squared value. And the R-squared value for our Roman numeral 2 or our exponential model is now at 97.7%. And again, wow, that's much closer to 100%. So what we're looking for is we want all these things to sort of, which one is our best model? Is 1 the best way to see a linear fit? Well, maybe not, because we said it was not linear. Is Roman numeral 2 the best way to see a linear fit? And then we just want to look at our third plot. And in our third plot, when you look at it, again, notice what they tell you. Log of price versus log of age. So now they're taking the log of both the x values and the log of the y values. So they're doing both, looking at this scatter plot. When you take the log of both, you are analyzing a power model. And so it has some sort of exponent to it. So some sort of power model. And you go through and you look at the same three things. When you look at, again, notice the plot. The plot is more linear than our original, but the plot is not as linear as our exponential model, as Roman numeral number 2. The residual plot, again, if you look at the residuals, so the residual plot actually looks like it has, again, a pattern to it. It goes sort of in that opposite use. So the residual plot appears to have a pattern. The values of your residuals are about the same as Roman numeral 2. And then if you analyze the r squared value for this one, it's high. I mean, it's 92.3%. But again, it's not as close to 100% as, again, our exponential model. So when you analyze or when you're given a whole bunch of data, you're looking at sort of these three pieces. You're looking at this original scatter plot of the data, you're looking at the residual plot, and then you're really looking at the r squared values in each. And that's going to help you answer the questions now on the second page. So since we have all of our notes over here, I'm just going to scroll now to the second page. So again, it says, number 1, explain how the information provided suggests that a linear model may not be appropriate for describing the relationship between car age and price. So for question number 1, this is actually our answer right here. The scatter plot, so rather than saying notice it, but you notice the plot is not linear. The residual plot has a pattern, and the r squared value is, again, not that close. I mean, it's close, but not as close as the others to 100%. So the answer to question 1 of how do we provide evidence that a linear model does not fit? Here it is. Here's all of that evidence for question number 1. For question number 2, would an exponential model or a power model provide a better description? So we've actually answered that as well. As we look at, again, what we wrote for exponential model and what we wrote for power model, we see that an exponential model is definitely the one that fits sort of better. Again, it's because when you transformed it, it was more linear, the residual plot was more scattered, the residual values were smaller, and our r squared was much closer to 100%. So for question 2, we would really expect the exponential model to provide a better description. And then again, it says use the information provided. We just kind of listed it again right here. So this is sort of your answer and justification for number 2. So then comes in questions 3 and 4. And questions 3 and 4 talk about we need to write an equation for the model. So when you write an equation for a model in question 3, you have to again note that we were looking at our exponential model. And typically our linear equations start off like this. And in our case, what did we do to the y in the exponential model? We took the log of y. And our y value in, again, our exponential model, if you're looking at the graph, was price. So this is the log of price. And again, they put the hat on it to say that it's predicted, equals, and then I'm going to go right back to that exponential model table. So I'm looking right in the table, and I want to look for a. And a is this first constant right there. So the 1.43723. The slope, the b, is this next value. So that would be negative 0.090652, and our x value was our age. So if you write it like this, you remember when we were doing the other class where it said define your variables? If you write it in your equation, then you're done. Question 4 now says, okay, we have it. Use our model you picked in question 2, exponential. We have the equation from question 3. Predict the price for a 5-year-old Ford Taurus. And now it's just a substitution problem. Being careful and noting that you have a logarithm in here. So again, just a substitution problem for question 4. And all you're doing is plugging in the age of that car, 5. Then you just simplify. So this minus this times 5. And I came up with 0.98397. And then here is sort of a review from pre-calc or transition to college. We need to get rid of a log to figure out our price. And the way that you get rid of a log is you're going to do the inverse. Inverse of a log is to take 10 and raise it to the power of both sides. What that does is it crosses out your log so that you're just left with price equals 10 to this exponent. And then you just plug that into your calculator. You actually get 9.638. Obviously, the car isn't going to cost you $9.64. You have to remember from the very beginning, your price is in thousands of dollars. So this represents $9,638 is your predicted price for a 5-year-old Ford Taurus, according to all the data that this gentleman has collected. So the reason, again, that we transform to linear is so that we can make some predictions. If we just used our original data, we would be very far off in what our cost for our car should be. And so by analyzing and deciding which model fits, then we can use the correct equation and, again, the correct log to find that value. We will be reviewing this again for a second day in class, so if you have questions, make sure that you bring them. Again, I highly suggest that you read through Chapter 12, both sections, and come in if you have any questions. Thank you.